El Hombre Grande 2.0.
This is the video demonstration of El Hombre Grande version 2.0. This is a starting point. There lies the end point. And this is the timer. And here we go. In 3, 2, 1. Go. This is the video demo for El Hombre Grande version 2.0. Here we see the starting point at 200 centimeters, and there's the end point. And here we see the stopwatch. And let's begin. And we're setting the timer in 3, 2, 1, go. Stop. And here's the timer at 8 seconds, 8.97 seconds. This is the video demonstration of El Hombre Grande version 2.0. Here we have the starting point set at 200 centimeters or 20 meters. There's the end point. And if we zoom in, we can see that the stopwatch is set at 000000. And without further ado, I will place this down to start the car and inform the timer when to start. And we're starting in 3, 2, 1, start. That's it. And here's the time at 7.59 seconds.
Alright, so before we talk about how hydrogen fuel cell works, let's just talk about its different parts and components. The side with the black connection, labeled H2, is called the anode side. So, as you can see on the diagram on the right, the side that is visible is the anode side. The side with the red connection, which is on the opposite side of the anode side, labeled O2, is called the cathode side. And the square-shaped layers towards the middle of the cell are called the catalysts. There's one on each side, and sandwiched in between the two catalysts. It's not really visible in the diagram, but sandwiched between those two is another square-shaped layer called the electrolyte. So now let's get on to how the hydrogen fuel cell actually produces electricity. So in the first step, hydrogen gas enters the cell through the anode side. Once it enters, it goes through the catalyst. If you've ever taken chemistry, you know that the ionization of an atom, which is when you break an atom into its atom protons and electrons, is an endothermic reaction. So the reaction has high activation energy, so you need a catalyst to lower this activation energy. So the catalyst layer lowers the activation energy, allowing this reaction to take place, and this is an oxidation reaction, and once the reaction takes place, you should be left with hydrogen protons and hydrogen electrons. And the reaction is written down here. So now let's move on to step 2 of this process. So you should probably know the layer in the middle of the cell is the electrolyte. It only allows positively charged hydrogen protons to travel through it. It does not allow the negatively charged ones to travel through it. So the negatively charged particles, or the negatively charged electrons, flow up here to the electrical current. And once they flow into the current, they go to power the motor. The positively charged particles pass through the electrolyte and travel towards the cathode side. Now let's move on to step 3. Alright, so oxygen. Oxygen enters through the cathode side and enters the catalyst layer. It combines with the hydrogen protons that pass through the electrolyte to form water, and the reaction is written down here if you're curious. The activation energy for this reaction is provided by the catalyst. This reaction is a reduction reaction. Water is a waste product of this reaction. It's not used for anything. It just exits the system. So let's move on to the process of electrolysis. So you're probably wondering, where do we get this hydrogen gas for the reaction from? Are we getting it from an external gas tank or something? No, we get it from a process called electrolysis. Electrolysis is pretty much the opposite of the process I just talked about. In this process, water enters through the positively charged side and enters the catalyst layer, and then it splits up into hydrogen protons and oxygen atoms. The catalyst layer provides the activation energy for that reaction. And the oxygen atoms exit the cell and go into a syringe where they're used later on. And the hydrogen enters the electrolyte. And if you remember, the electrolyte in this cell only lets hydrogen protons through, so it passes through the electrolyte, enters the catalyst layer on the opposite side, where it combines with electrons from the electrical current that is running through the cell, and when these protons and electrons combine, it forms hydrogen gas, which exits the cell and enters the syringe, and this hydrogen gas, which is stored in the syringe, later can be converted into electricity to power the motor and make the car move. So now let's talk about using fuel cells as a sustainable energy source. So climate change is obviously a really big issue in general and in today's political climate, and cars are the second largest source of pollution. So hydrogen fuel cells could, in theory, be a viable alternative to standard gas-powered engines, because fuel cells do not produce any CO2 gas, and the only form of exhaust a fuel cell produces are water vapor and heat. Fuel cells also don't require fossil fuels to produce energy. They run entirely on H2 gas, although it is true that electricity is required for electrolysis in order to produce H2 gas, and that electricity probably comes from fossil fuels, but renewable energy sources such as windmills can be used to provide the electricity needed for electrolysis. Now let's compare hydrogen fuel cells to another renewable energy source that can be used for motor vehicles. Car batteries, or electric batteries. Electric battery engines run obviously on electricity. The electricity that powers most electric cars that are on the road today unfortunately does come from fossil fuels, but renewable energy sources can be used in lieu. Batteries have around 70 to 80% efficiency, but their range is very, very short. Most cars powered with batteries can only go around 200 miles without charge. Fuel cells, on the other hand, run on hydrogen gas that is produced through electrolysis. Electrolysis still requires electricity, as I was previously explaining, and that electricity will probably come from fossil fuels, since that's where 80% of our electricity comes from. However, you could also get this electricity from renewable sources. Furthermore, the efficiency of a fuel cell is much worse than a battery at 25 to 35% on average. But the range of cars powered by a fuel cell is longer than a car powered on battery. It's around 300 miles. While a fuel cell isn't as efficient as a battery, electrolysis does not use as much electricity. Studies from Volkswagen have found that a hydrogen fuel cell uses less electricity than a battery-powered engine uses. So hydrogen fuel cells may be a viable alternative to gas engines and electric-powered engines for the purpose of combating climate change. So now let's just talk about some additional research we did. So we did some research into aerodynamics, and we found that when the car moves, it pushes on the air, so the power produced by the motor that propels the car forward is repelled with air resistance. We can minimize the amount of air resistance by designing the car in a way where the air slides up the car instead of encountering it head-on. We also did some additional research on friction and energy, and we figured out that there needs to be some friction between the tire and the ground, but not too much, or else the car won't move. We also found that the less friction there is between the axle and the bearing, the faster the car will move. So now let's move on to some brainstorming. So during the brainstorming process, we thought of two potential designs by doing some research online. The design on the left, here's the picture. This is the first design we thought of. It's a leaf-shaped design where the fuel cells are vertically mounted, and we analyzed the pros and cons of the design, and we concluded that this design is good because it's aerodynamic and it has bigger wheels, but it also may be problematic because it's hard to balance. This design on the right is the second design we thought of. This is a pretty basic design, nothing too intricate here. The fuel cells will be mounted on the back in lieu of these water tanks, and we thought that we could maybe 3D print this if school opened up and we had access to the school's 3D printers. After going through the brainstorming process, this is the final design we decided on. In this design, the front is pointy so that the car is more aerodynamic. The fuel cells are mounted towards the center so that the weight of the car is distributed very evenly, and the motor is mounted towards the back. And in this design, the chassis is made of cardboard, and the bearings used are straws. So now let's move on to some experimentation we did with different gear ratios. So in this experiment, we tested out 5 different gear ratios: 60 to 30, 30 to 10, 10 to 10, 10 to 30, and 30 to 60. And the goal of this experiment was to see which gear ratio would provide us with the fastest speed for a car powered by dual fuel cells. This was done across a distance of 1.51 meters, and we did it with the wooden prototype shown on the right. And these are the results of the the gear ratio experiment, we found that the 60-30 gear ratio was the fastest and the 30-60 gear ratio was the slowest. And this kind of shows that larger gear ratios are better because there's more torque. So 50-10 gear ratio was used. We also did some additional research on electrical connections and circuitry, and we concluded that parallel circuits would actually work the best because voltage is conserved, whereas in a series circuit, voltage is not conserved. And this is a diagram, or not a diagram, but a picture of the wiring of our car. So as you can see in this diagram, or picture, the cathode side is hooked up to the cathode side, and the cathode side, to be specific, is the H2 side. The H2 sides are hooked up via this black wire, and the O2 sides, which are the anode sides, are hooked up via this red wire. And in this picture, the cells aren't connected to the motor, but if they were, a wire would be attached to one pin of the motor going to this exposed part of the red wire, and a wire would be attached to the other pin of the motor going to this exposed part of the black wire. So that's basically how our wiring would work. So now let's go over the materials we used to craft the chassis. We used cardboard specifically to craft the chassis, and the reason we used cardboard is because it's super lightweight and it's very easy to procure. Because we're in a virtual setting, we can't go to our school makerspace for materials. We have to kind of use what we have at home, and we had tons of cardboard, so we used cardboard. The only real con is that cardboard is super fragile. It bends very easily. But we were very careful while handling the car so that the cardboard wouldn't bend. These are some of the other materials we use. You can pause and read. The list is way too long to go through. Alright, so now let's go through the steps we followed to actually create our car. First, we started with a cardboard box. Here's the picture. Then we cut this cardboard box using an Exacto knife, and this is the shape we cut it into. It's a rectangular shape with a triangle on one side. And then after that, we attached the wheels and the bearings. For bearings, we use straws. We attached the wheels and the bearings onto the car, and then we super glued the motor onto the chassis. So as you can see, here's the picture after step 3. And in step 4, we made a spoiler, which was placed on the back of the car. And the spoiler was made with cardboard. And as you can see, the spoiler is circled in red over here. We basically created the spoiler to hold the syringes, and we inserted the syringes into the spoiler. In step 5, we attached Velcro to the car, to the center of the car, and we attached the fuel cells to the car using the Velcro strips. So as you can see, the fuel cells attached to the car. And then in step 6, we just connected the syringes and the motor and everything together. And we also wrote our car's name all over it.